Hello, everyone. Thank you for your time and for attending this talk. My name is Shengzhe. Today, I'm going to share our synthetic net flow data generation work, which I worked on along with Manish Marwah, Martin Arlitt, and my advisor, Naren Ramakrishnan. The work I'm representing today focuses on generating synthetic network traffic data with generative neural models. We call it STEM. So cybersecurity is of increasing importance during the past decade, even in our daily life. People spend a lot to stop cyber attacks. As one of the most powerful tools, deep learning models have achieved great success in cybersecurity applications. Given a large quantity of available data, deep learning methods appear to be a good fit. However, although large amounts of data is available to security teams for cybersecurity machine learning applications, it is sensitive, and access to it can result in privacy violations. Thus, it is difficult for data scientists to obtain realistic data to train their models, even internally within an organization. People have tried to use data anonymization or data perturbation, but both of them have their flaws. In this paper, we take an orthogonal approach. We generate synthetic data that is realistic enough to replace real data in machine learning tasks, but not the same one with the real data. Here is an example format of network traffic data, so-called net flow. To reach the goal, we need to overcome several challenges. First, how to capture the complex dependencies across both rows and columns. Here, the rows are time series, and the columns should not be considered isolably. Secondly, the column attributes can be homogeneous and have multiple data types, such as continuous, numerical, and categorical. Note that what we want to generate is not a deterministic value, but probability distributions. Thirdly, unlike standard data format as image, evaluating the quality of the generated net flow data is the other key challenge. Assuming a dataset D historical is used to train the generative model, and an unseen test dataset D test is used to evaluate the performance of the generative model. We use two criteria to compare the generated data D synthetic with D test. The first one is the similarity between a metric M evaluated on the two datasets. And the second is the similarity between performance P on training the same machine learning task T, in which the real data D test is replaced by the synthetic data. Peers have been working on generating network-related data. In the beginning, they only generate temporal independent data, while some recent works start to consider the temporal naturalness under GAN's architecture. We think there are three advantages in STANS architecture. The first, conditional GANs capture the temporal dependencies with block-based conditions, or when time series is long. While autoregressive generation has a continuous and consistent form of temporal condition capturing. Second, STANS architecture can support more flexible prediction data types, and hence can generate more domain semantics like IP addresses and port numbers. Third, autoregressive generative neural models have explicit likelihood to track. Well, how to accurately evaluate likelihood on GANs is still an open question. We also stand on the shoulders of the predecessors. Autoregressive series deep learning models offer the direction of generating time series data, such as pixel RNN for image and WaveNet for music. While mixed density network researchers offer the capability of learning multimode distributions in neural manner. Here is how we consider to solve the problem. We assume the data to be generated is a multivariate time series. Specifically, dataset X contains n rows and m columns. Each row xi is an observation at time point I, and each column j is a random variable j. Such data X follows an unknown high-dimensional joint distribution Px, which is infeasible to directly estimate. The goal is to estimate Px by a generative model S, which returns the dependency structure across rows and columns. Values in a column typically depend on other columns, and temporal dependence of a row that can extend to many prior rows. Once Model S is trained, it can be used to generate an arbitrary amount of data. As the figure shows, we iteratively generate a row at a time, then put it as a condition of the next row. Each element in the time window may affect all variables distributions in the upcoming rows. For each attribute column, we learn the model with different neural components and different loss back propagation. Next, we show our neural architecture components. First, Stan uses multiple convolutional layers that preserve the spatial and temporal resolutions in a sliding time window box. We call it window CNN, since they operate on a sliding window of data and perform a two-dimensional convolution. For one row xi, the layer captures a near rectangular context above the row. Secondly, a window CNN connect to either Gaussian mixture layers or softmax layers separately for generating continuous or discrete attributes. The special component Gaussian mixture layers here learns a conditional Gaussian mixture distributions. It consists of three parallel fully connected layers modeling alpha I, sigma I, and mu I separately. Furthermore, IP addresses and port numbers are key to network traffic data. However, naively modeling them as continuous or discrete variables gives poor results. Stan specifically learn IP addresses and port numbers characteristic. Stan treat an IP address as 4 256 categorical discrete attributes. With the help of the Stan mask definition, even though one IP address attribute is split across 4 intermediate attributes, it is considered together as one variable for attribute dependence. Note that such setting is just a config parameter, and the mask mechanism helps improve all types of attributes, but not just IP. Since port number can vary between 0 and 64K, that is too many values to model as a discrete variable. On the other hand, treating it as a continuous variable would result in inaccuracies, especially for well-known ports, those less than 1024, where being off even by 1 can mean something completely different. Therefore, we take a hybrid approach. Stan treat port numbers up to 1024 individually as discrete values. Beyond that, it models ports in bins of size 100. Okay. The evaluation of generative models is challenging and subjective. Recall our strategies. We use multiple metrics to compare them. First, the likelihood function measures the goodness of a statistical model fitting a data sample. Also, JS divergence shows a marginal distribution similarity. Second, one of the domain knowledge check is the unique IP address, and the unique IP volume distribution should follow power law. Third, similarly, stan generated data that can learn the semantic between protocol and port number. For example, port number 53 for DNS service should be the most frequently occurring UDP port in practice. Fourth, we summarize 5 domain knowledge tests. For short, we tested the data with multiple perspectives, like validity of IP addresses, relationship between bytes and packets, etc. Last, we test our synthetic data on 2 cybersecurity machine learning applications to detect anomalies using self-supervision. The one is the regression forecasting task, and another one is classification prediction task. The F1 score and mean square error shows the application models keep a good performance, even training with the full stan synthetic data. In summary, our proposed stan generates realistic synthetic network traffic dataset for subsequent machine learning applications, and current results are encouraging. For the future work, we believe the privacy preserving is still important. A robust evaluation should be well developed so that no training data is leaked in the generated data, and no training data is memorized inside the model. That is my slides today, and thank you for watching. Yeah, thank you again.